So good day everyone. So in this video presentation I will be discussing one of the most fundamental concepts in calculus, which is the limit theorems. So before we start, let's first understand what a limit actually means. In mathematics, the concept of a limit helps us describe how a function behaves as the input values get closer and closer to a certain point. It is like asking what values does this function approach. Even if it doesn't exactly reach that point, limits are the foundation of other concepts in calculus, such as continuity, derivatives, and also the integrals.
Now, sometimes, solving limits directly can be confusing or complicated, but that's where limit theorems comes in. This theorem gives us a set of rules that make finding limits easier and more systematic. Instead of guessing or doing trial and error, we can just apply the correct rule of the limits.
For example, we have simple ones like the constant rule, which says that the limit of a constant is just the constant itself, and the identity rule, which tells us that the limit of x as x approaches to a is simply a. Then, we also have rules that involve operations such as sum and difference rule, product rule, quotient rule, and even root and power rules. Each of these theorems allow us to handle more complex functions step by step. They basically serve as our toolbox when evaluating limits efficiently and accurately. So in this lesson, we will go through each theorem from the constant rule up to the root rule and understand their meanings, formulas, and how we can use them in solving problems.
So there are 10 important theorems that we will cover in this discussions. So the first theorem or the theorem 1.0, which is the constant rule theorem. So the limit theorem 1.0, which is the constant function rule, tells us that the limit of the constant as x approaches to a is just equals to constant. So what does this mean? So the limit of a constant is equal to the constant itself. So the constant function rule is one of the simplest limit theorems in calculus and is also one of the most important building blocks. These rules tell us that when we take the limit of a constant function as x approaches any number, the result is simply the constant itself. So this means that a constant function is a function that always returns the same value no matter what the input is. Now, let's imagine this one. So imagine you are walking along a perfectly flat road that always at a height of 7 meters. No matter where you walk, whether you go toward 5 meters, 10 meters, or 20 meters on the horizontal axis, your height stays the same, which is the 7 meters. So as you get closer to any point on the horizontal line, your vertical position doesn't change, and that's exactly what this theorem is telling us. So given this example, which is the f of x is equals to 7. So what does the constant function theorem say? So f of x is equals to c, where c is a constant, then for any value of a. So let's go back to the formula, which is the limit of the function as x approaches to a is equals to the constant. So in our example, the function is f of x is equals to 7. This means that no matter what value of x you plug in, the output is always 7. It doesn't matter if x is equals to 1, 10, negative 1000, or even if x approaches to a, the output stays 7. So the limit of a constant function is just the constant itself. So in this example is where we're given that the limit of 10 at x approaches to negative 3. So our c here or our constant is 10 and our x here is negative 3. Using the theorem formula, the limit of c as x approaches to a is equals to c. So limit of 10 as x approaches to negative 3 is just simply 10. This states that as x gets closer to negative 3, the value of the function does not change. Now for our second limit theorem 1.1, which is the identity rule. So what does this limit theorem 1.1 the identity function rule states. So given that the limit of x as x approaches to a is equals to the a, given that this a is a real number. So what does this theorem means? This means that the limit of x as x approaches to a is equal to a. This is known as the identity rule for limits, wherein it tells us that when you're finding the limit of the variable x as x approaches a number a, the result is just a. In other words, the function simply returns to the input value. So the limit just follows where x is going. So if you walk along the x-axis toward any value a, your output is also getting closer to a, since the input equals the output. So in this example number 1, which is the theorem 1.1, the identity function rule, to understand a simple example which is the limit of x as x approaches to positive 3. So what does the identity function rule say to this? So if f of x is equals to x, then the limit of x as x approaches to a is equals to a. It just means that as x gets closer to a, the function value also gets closer to a. So in our example, the function is f of x is equals to x, the point we're approaching is x is equals to 3. So we ask, as x gets closer to 3, what does f of x get closer to? Since f of x is x, the answer is simply limit of x as x approaches to 3 is equals to 3. Note that whenever you take the limit of x as x approaches to a number, the result is just the number. That's why it is called the identity function, because f of x is equals to x. Let's have this example number 2. So given that the limit of x as x approaches to negative 8, so using the identity rule, so limit of 8 or limit of negative 8 as x approaches to negative 8 is just simply negative 8. So since the function just return to an x and x is approaching to negative 8, therefore the limit is simply negative 8. Now we are already done discussing the constant function rule, which is the limit 1.0, and also the limit 1.1, which is the identity rule. So this plays a pivotal role for us to understand this following limits. It is because this helps us to understand and answer it accurately and reliable. Since we are already done with the limit 1.1, let's proceed to the limit theorem 1.2, which is the constant multiple rule. It says that if a limit of f of x as x approaches to a is equals to L and c is a constant, then the limit of x as x approaches to a is simply c multiplied by f of x is equals to c multiplied by L. So this means that the limit of a constant times a function is equal to the constant times the limit of the function. So where c is a real constant, f of x is a function with a limit as x approaches to a, and a is any real number. So this means that a constant multiple rule tells us that if a function f of x has a limit as x approaches a number a, and if we multiply that function by a constant c, then we can pull out the constant and multiply it by the limit of the function. So in mathematical terms, this means that the limit of a constant times a function is equals to the constant times the limit of the function, because a limit focuses on what the output of a function is getting close to as x approaches to a. So the new limit becomes the c multiplied by L, which means that c is our constant and L is our function of x. So in our example number 1, given that the function is f of x is equals to 4x, we can take of this as 4x is equals to 4 times x. But here is 4 is our constant and x is our identity function. We already know that the identity function rule that limit of x as x approaches to 2 is equals to 2.
So applying the constant multiple rule, so limit of 4x as x approaches to 2 is equals to 4 times limit of x as x approaches to 2 is equals to 4 times 2, which is, if we multiply 4 times 2, is equals to 8. So the answer is the limit of r for x as x approaches to 2 is equals to 8. So let's have this another example number 2. So given that the limit as x approaches to 1 is negative 3x squared, so we have also to apply the theorem. So negative 3 times limit of x as x approaches to 1 is x squared. So negative 3 multiplied by 1 squared. So we all know that the 1 squared is just simply 1. So negative 3 times 1 is equals to negative 3. So limit of negative 3x squared as x approaches to 1 is simply negative 3. Now you already understand the constant multiple rule. So let's move on to the theorem 1.3, which is the sum and difference rule. The sum and difference rule is the limit of the sum or difference of two functions is the sum or difference of their limits. So the sum and difference rule tell us that if the individual limits of two functions f of x and g of x exist as x approaches in number a, then the limit of their sum is the sum of their limits, or the limit of their differences is the differences of their limits. So this rule allows us to split up limits over addition and subtraction, making it much easier to compute complicated limits by handling each part separately. So to fully understand, and let's have this example number 1. So given that f of x is equals to x squared and g of x is 3x, then the limit as x approaches to 2 is x squared plus 3x. So using the theorem, which is sum or difference rule, so the limit as x approaches to 2 is x squared plus limit as x approaches to 2 is 3x. So substituting the x as 2, since x approaches to 2 is 2 squared plus 3 multiplied by 2. So that is 2 times 2 is equals to 4 plus 3 multiplied by 2 is equals to 6. So 4 plus 6 is equals to 10. So therefore, the limit of x approaches to 2, x squared plus 3x is equals to 10. So let's have this another example number 2. Given that f of x is equals to 5x and g of x is equals to x squared, the limit as x approaches to 1 is equals to 5x minus x squared. So still using the theorem, so limit as x approaches to 1, 5x minus limit as x approaches to 1, x squared. So we all substituting the value of x. So 5 times 1 minus, since our x is 1, so 1 squared. So 5 times 1 equals 5 minus 1 multiplied by itself is just 1. So 5 minus 1 is equals to 4. Therefore, the limit as x approaches to 1, 5x minus x squared is equals to 4. So since we are done with the sum and difference rule theorem, let's proceed to the theorem 1.4, which is the extended sum rule. So the extended sum rule, so this rule applies the same principle to more than two functions added or subtracted together. So the extended sum rules is the generalization of theorem 1.3, the sum and difference rule, while theorem 1.3 handles two functions being added or subtracted. So this rule extends it to any number of the function. So what does this mean? So if you have a limit of a sum of several functions, say that 3, 4, or even more, you can take the limit of each part separately, then add them all together. As long as each individual limit exists, you are allowed to split the big expression into smaller, manageable pieces. So remember, when dealing with sum of many functions, this rule lets you take it one step at a time. So let's have this example number 1. So given that the limit as x approaches to 1, 2x plus x squared minus 3x cubed. So as you can see in the expression is, you can see that we have a more than 2 function. It is because we have 3 function at the same time. So using the extended sum rule theorems, we can solve this or turn this into smaller pieces and manageable kind of expression. So applying the limit as x approaches to 1, 2x plus limit as x approaches to 1, x squared minus limit as x approaches to 1, 3x cubed. So the next one, after we separate the expression, is we have to substitute the value of our x, or our x approaches to 1. So the limit as x approaches to 1, 2x, so this became 2 multiplied by 1. It is because our x is 1. Plus our limit as x approaches to 1, x squared became 1 squared, minus the limit as x approaches to 1, 3x cubed became 3 times 1 cubed. So we all know that 2 times 1 is equals to 2 plus the 1 squared. If we multiply 1 by itself, it became only 1 minus 3 times 1. It is because the cube of 1 is simply 1. So 2 plus 1 is equals to 3 minus 3 is equals to 0. So therefore, the limit as x approaches to 1, 2x plus x squared minus 3x cubed is equals to 0. So let's have this another example, example number 2. So the limit as x approaches to 2, x squared plus 4x plus 5. So what are we going to do with this? Since it is belong to the limit theorem 1.4, the extended sum difference rule. So first is we have to separate this expression using the theorems. So this becomes limit as x approaches to 2, x squared plus limit as x approaches to 2, 4x plus limit as x approaches to 2 plus 5 is equals to, since we have to substitute the value of our x, because as x approaches to 2, so our value is approaching to 2. So our x there is 2. So this became 2 squared plus 4 times 2 plus 5. It is because our value of our x is 2. So 2 squared is just simply 4 plus 4 times 2 is equals to 8 plus 5. So if we add 4 plus 8 plus 5, so this becomes 17. So therefore, the limit as x approaches to 2, x squared plus 4x plus 5 is equals to 17. Now, we are already done with the extended sum rule theorem. Let's proceed to the theorem 1.5, the sum and difference of many functions. The limit of several functions added or subtracted is equal to the sum or difference of their individual limits. This is a general case of the last few theorems. It says that if we have a limit involving multiple functions added or subtracted together, we can take the limit of each piece individually and then combine the result using the same operations. Theorems 1.5 is essentially a combination and extension of the previous theorem, specifically Theorem 1.3, the sum and difference rule, and 1.4, the extended sum rule. If you have a limit involving multiple functions being added or subtracted, you can take the limit each function separately and then perform the same addition or subtractions on the results. So to fully understand this one is, let's have an example number 1. Given that the limit as x approaches to 2, x squared minus 3x plus 7. So we have to separate using the theorem 1.5, the sum and difference of several function. So how to do it? So applying the limit as x approaches to 2, x squared minus limit as x approaches to 2, 3x plus limit as x approaches to 2, 7. So we have to substitute the value of our x to the following expression. So x squared became 2 squared minus 3x became 3 multiplied by 2 plus 7. Since 7 don't have the variable of x, so 2 squared is equals to 4 minus 3 times 2 is equals to 6 plus 7 is equals to 4 minus 6 plus 7. So 4 minus 6 is negative 2 plus 7 equals negative 2 plus 7 is simply 5. So therefore, the limit as x approaches to 2, x squared minus 3x plus 7 is equals to 5. Next, let's proceed to the theorem 1.6, the product rule. The product rule is the limit of a product of two functions is equal to the product of their individual limits. The product rule for limits tells us that if the limits of two functions exist individually as x approaches some number a, then the limit of their product is just the product of their limits. This is valid only when both individual limits exist. So how does this work? This rule works because as x approaches to a, the function values f of x and g of x each approach a number. Multiplying two numbers that get closer to a specific values will give a product that also gets closer to the product of those values. This means you don't need to multiply out the full expression first. You can take the limit separately, then multiply. So to fully understand this theorem, let's give an example number 1. So let f of x is equals to x squared and g of x is equals to 3x. So find the limit as x approaches to 2, x squared times 3x. First is let's use and apply the product rule theorem. So it is equals to limit as x approaches to 2, x squared times limit as x approaches to 2, 3x. So applying the substitution for the x is, since it is x squared, so this becomes 2 squared times 3 multiplied by 2. Since 3x is simply our x is 2, so 3 multiplied by 2. So 2 squared is equals to 4 times 3 times 2 is equals to 6. So therefore, 4 times 6 is equals to 24. Therefore, the limit as x approaches to 2, x squared minus 3x is equals to 24. Since we are done with the theorem 1.6, which is the product rule, let's proceed to the theorem 1.7, the product or multiple rule. Theorem 1.7, the product or multiple rule. When there are more than two functions multiplied together, the limit of the product is the product of all their limits. Theorem 1.7 is an extension of Theorem 1.6. The product rule, it tells us that if you are taking the limit of a product of 3 or more functions, you can find the limit of each function separately. Then, multiply them all together. This is just like the product rule, but applied to many factors instead of just 2. All individual limits must exist and must be finite in order to apply this rule. So for this example, in order for us to fully understand the limit theorem 1.7, the product of multiple functions, let's have this example number 1. So let f of x is equals to x and g of x is equals to x plus 1 and h of x is equals to x. Find the limit as x approaches to 1. Find the limit as x approaches to 1 as x multiplied by x plus 1 times 2x. First, let's apply the theorem. So limit as x approaches to 1, x times limit as x approaches to 1, x plus 1 times limit as x approaches to 1, 2x. Now, let's substitute the value of x. So, x is simply 1, so 1 times 1 plus 1 times 2 times 1. So, 1 times 1 plus 1 is equals to 2 times 2 times 1 is equals to 2. So 1 times 2 is equals to 2 times 2 is equals to 4. So therefore, the limit as x approaches to 1, x times x plus 1 times 2x is equals to 4. Now we are done with the theorem 1.7. Let's proceed to the theorem 1.8, which is the power rule. The limit of a function raised to a power is equal to the limit of the function raised to that same power, where n is a positive integer and sometimes extended to real exponents. The limit x approaches to a must exist. The power rule tells us that if a function f of x has a limit as x approaches to a, then raising that function to a power n will also have a limit. And we can simply raise the limit of the function to that power. This is extremely helpful when dealing with functions involving squares, cubes, and other powers. What makes this rule useful? You don't have to expand complicated powers like x plus 4 raised to 4. You can evaluate the inner limit, then raise the result to that equal power. It saves time and makes solving limits of polynomial or rational function much easier. Note that the power rule in limit is not valid for negative powers if the function approaches to 0, because that would mean dividing by 0, which is undefined. And that's what makes some of the negative powers for this theorems is undefined or sometimes indeterminate. So to further illustrate the limit theorem 1.8, the power rule, let's have first an example number 1. So in this example is we will be examining and using the limit theorem 1.8, in which we can provide that n power can be useful using the inner expression or computing first the inner expression. So first is we have to evaluate the inner limit. So limit as x approaching to 2, x plus 1 cube. Since as you can see that x is approaching to 2, so we have to substitute the 2 to the value of x. So it becomes 2 plus 1 cube. So 2 plus 1 is equals to 3, then cube. So now we have to apply the theorem, which is the power rule. So the cube of 3 is simply 27. It is because 3 times 3 times 3 is equals to 27. Therefore, the limit as x approaches to 2, x plus 1 cube is simply 27. Now we are already done with the theorem 1.8, which is the power rule. Now let's proceed to the theorem 1.9, the quotient rule. Theorem 1.9, the quotient rule. The limit of a quotient is equal to the quotient of their limits, provided the denominator's limit is not 0. The quotient rule tells us how to find the limit of a fraction made from two functions. If both the numerator and the denominator have limit as x approaches to a, and the limit of the denominator is not 0, then we can separately take the limits of the top and bottom and divide the results. So here is the important conditions for the quotient rule. The denominator's limit must not be 0. If it is 0, the expression becomes undefined or indeterminate, and you must use algebra or L'Hospital rule. So why is this useful? So this rule simplifies working with rational functions, fractions of polynomials for example, letting you evaluate each part separately instead of dealing with the entire fraction at once. Let's have this an example number 1. Find the limit as x approaches to 2, x squared plus 1 over x plus 3. So what we are going to do is let's first simplify the inner limit. So the step 1 is
we have to determine the numerator and also the denominator so that we're able to know what are the functions or the expression that needs to be simplified. So our numerator here is f of x is equals to x squared plus 1, and our g of x is equals to x plus 3, which is our denominator. And for the step 2 is we have to take the limit in each expression. Now, to simplify the numerator and denominator is we take the limit in each expression. So limit as x approaches to 2, x squared plus limit as x approaches to 2, 1 over, next is we have to take the limit of the denominator. So limit as x approaches to 2, x plus limit as x approaches to 2, 3. Now we have to simplify and substituting the value of our x. So this became 2 squared plus 1 because 1 didn't have any value of x. So our x is 2 plus 3. So therefore, we have to simplify this one. So 2 squared is simply 4 plus 1 over 2 plus 3 is equals to 5. And we have to simplify the denominator and the numerator. So 4 plus 1 is equals to 5 over 5. So 5 divided 5 is simply 1. So therefore, the limit as x approaches to 2, x plus 1 over x plus 3 is just equal to 1. So since the denominator limit is not 0, therefore we could have the limit of x approaches to 2, x squared plus 1 over x plus 3 is just equal to 1. Now, we will proceed to the last theorem, the theorem 1.10, the root rule. Theorem 1.10, the root rule, the limit of the root of a function is equal to the root of the limit of the function, provided that the limit exists and the root is defined. The root rule tells us if the limit of a function f of x exists at x approaches to a, and taking the nth root of that function makes sense. The root is defined and real. Then we can take the limit inside the root. This rule allows us to simplify limits that involve square roots, cube roots, or any other nth root. So important condition for the root rule. The limit f of x must exist. The root must be defined. For even roots, square roots, the expression under the root must be non-negative or greater or equal to 0. For odd roots, like cube roots, you can take roots of negative numbers, so it is always defined for real numbers. So to further understand this one, as we have here the example number 1, the limit as x approaches to 4, square root of x plus 5. So first is, what are we going to do is to look and to simplify the inner limit, which is the square root of x plus 5. First is we have to take the limit inside of the expression. So this became square root of limit as x approaches to 4x plus limit as x approaches to 4, 5 is equal to, so here is we have to simplify the inside, and since our value of x is 4, so therefore let's exchange the x into 4. So square root of 4 plus 5. Then we have to add the 4 and 5. So 4 plus 5 is equals to 9. Then square root of 9. So here is we have to apply the limit theorem, which is the root rule. So we have to take the root or the square root of the 9. So since the square root of 9 is equals to 3, it is because 3 times 3 is 9. So therefore, the limit as x approaches to 4, square root of x plus 5 is equals to 3. Together, these theorems form the foundation for solving limit problems. They allow us to simplify complex expressions and evaluate limits systematically, making our calculation clearer and more reliable. I hope that you have learned something from the 10 theorems, and at this next part is you're going to answer some of the exercises, and let's check if what are the theorems applied to that exercises. So for the exercises, number 1 is limit x approaches to 1 2x squared plus 3x 1 over x plus 4. So first is we have to simplify or take the limit in the inside of the expression of, so limit as x approaches to 1 2x squared plus limit as x approaches to 1 3x minus limit as x approaches to 1 1 over limit as x approaches to 1x plus limit as x approaches to 1 4. So let's substitute the value of our x, which is 1. So 2 times 1 squared plus 3 times minus 1 over 1 plus 4. So since the 1 times 1 is to 1, so therefore 2 times 1 p minus 1 over 5. So 2 times 1 is equals to 2 plus 3 minus 1. So let's simplify it. So 2 plus 3 is equals to 5 minus 1 over 5. So 5 minus 1 is equals to 4 over 5. Therefore, the limit as x approaches to 1, 2x squared plus 3x minus 1 over x plus 4 is equals to over 5. So here is the theorems that was being used.
So let's take a look to the exercises number 2, given that the limit as x approaches to 2, square root of 3x squared minus x. So what are the first that we are going to do is to apply the theorem 1.5, which is the sum and difference rule. So first is let's simplify the limits, which is if we take the limit as x approaches to 2, 3x squared minus limit as x approaches to 2x. So now let's substitute the value of x. Since our value x is 2, or we say that x is approaches to 2, so let's give that the value of x is our 2. So square root of 3 times 2 squared minus 2. So let's simplify. So 2 times 2 is equals to 4. What makes it 3 times 4 minus 2. Then we all know that 3 times 2 is equals to 12 minus 2. So this became square root of 12 minus 2. So now we all know that if we multiply 12 by negative 2, so this makes us square root of 10. And since we don't have, or we can say, or there is no perfect square root for 10, so our answer is square root of 10. So the limit x approaches to 2, square root of 3x squared minus x is equals to square root of 10. Now let's proceed to our exercises number 3. So given that the limit as x approaches to 1, x squared plus 2x plus 1 times x minus 1 over x plus 1. The first that we have to do is we could factor the x squared plus 2x plus 1 into x plus 1 squared. So our limit becomes limit as x approaches to 1, x plus 1 squared times x minus 1 over x plus 1. So since we can cancel out the x plus 1 to the numerator and denominator, so the remaining limits or the function expression that we have, limit as x approaches to 1, x 1 and x minus 1. Since we already cancel out the x plus 1 numerator and also the denominator. And let's apply the theorem 1.6, which is the product rule. So let's take the limit of these two expressions. The limit
x approaches to 1, x plus 1 times limit x approaches to 1, x minus 1. Then let's substitute the value of our x, which is 1. So 1 plus 1 times 1 minus 1. So we all know that 1 plus 1 is equals to 2 and 1 minus 1 equals to 0. Then let's multiply 2 times 0. So we all know that 2 times 0 is equals to 0. Now limit as x approaches to 1, x squared plus 2x plus 1, x minus 1 over x plus 1 is equals to 0. So let's have this exercises number 4, which is the limits x approaches to 0, 2x plus square root of x squared plus 1 minus 1 over x. So as you can see, we have to choose this one on how to calculate the direct substitution and also simplifying before we apply limit. So first is let's take if we could get the limits of this function given that we have to direct substitute it. So limit as x approaches to 0, 2x plus square root of x squared plus 1 minus 1 over x. We have to substitute the x approaches to 0. So limit 2x as x approaches to 0 plus square root of limit x approaches to 0 x squared plus limit as x approaches to 0 1 minus limit as x approaches to 0 1 over limit x approaches to 0 x. So this being if we substitute the value of x, so 2 times 0 plus square root of 0 squared plus 1 minus 1 over 0. So if we simplify, so it became 0 plus square root of 0 plus 1 minus 1 over 0 plus, so then simplify, so this became 0 plus square root of 1 minus 1 over 0. So the square root of 1 is simply 1. So this became 0 plus 1 minus 1 over 0. Since 0 plus 1 is equals to 1 and 1 minus 1 equals to 0, so 0 over 0, this became a indeterminate or undefined. So this means that substitution could lead us to our indeterminate or undefined limits of functions. So as you can see, direct substitution could lead to indeterminate. So what we are going to is to simplify first the expression. So limit as x approaches to 0 is we could simplify the 2x plus square root of x squared plus 1 minus 1 over x into limit as x approaches to 0, separate or splitting the denominator. So this will make 2x over x plus square root of x squared plus 1 minus 1 over x. Then apply the theorem 1.4, the sum rule. So limit as x approaches to 0, 2x over x could cancel both sides of the x, remaining the plus x squared plus 1 minus 1 over x. Now let's apply the theorem. Let's take the limits of each expression. So limit as x approaches to 0, 2 plus square root as limit as x approaches to 0, x squared plus limit as x approaches to 0, 1 minus limit as x approaches to 0 over limit as x approaches to 0, x. So this became 2 square root of 0 squared plus 1 minus 1 over 0. So simplify, so this became 2 plus square root of 0 plus 1 minus 1 over 0. Then if we add 0 plus 1, so this became 1. So this becomes 2 plus square root of 1 minus 1 over 0. So we all know that the square root of 1 is simply 1. So this became 2 plus 1 minus 1 over 0. So we could get 2 plus 1. So since 1 minus 1 is equals to 0, so this became 0 over 0 is equals to 2 plus 0, because 0 over 0 is simply 0. So this means that 2 plus 0 is equals to 2. So by simplifying the expression, we could have a real number value of these limits.